Okay, let's talk a little bit about section 6.1. This is going to be my present. This is a repeat of what I did in class. This is a presentation on 6.1. One of the things in there is about arc length. So, the way I approach presenting that is I said, I drew a graph of the line that went through 1 and had a slope of 2. And said, how far is it from minus 1, 1, minus 1, minus 1 to, see, it goes through 0, 1, 1, 3, and 2, 5. Reminding you of how we find the distance between points. And some people in the class said, well, that's the change in x squared plus the change in y squared square root. Pythagorean theorem. The x changed by 1, 2, 3. The y changed by 2, 4, 6. And so we got 9 plus 36, square root of 45 is the distance between them. Okay, so then I said, what if it wasn't a straight line, but it was a curve, like on a parabola, which goes through 0, 0, 1, 1, and 2, 4. How far, if you follow the curve, is it from 0, 0 to 2, 4? Well, it's not a straight line, so it's a little harder to do. But if you break it into little tiny chunks all the way along the way, zooming in on it, we would be doing change in y and change in x and change in y. We'd be doing little tiny changes in y's, changes in x, and changes in y, and calculating the distance between those 2 points and then the next 2 little points close together. And we would do it for smaller and smaller segments, which sounds like calculus. So if I take this formula for doing little short lines, and I take and factor out a delta x, then delta x inside would be x squared, delta x squared, so outside it's just delta x. This would be 1, but I have to factor it out of this, so I'd have delta y divided by delta x squared, because they're inside. Outside it's just delta, but inside it's a square. And so this would be, I'd take the change in x times the square root of 1 minus the change in y over the change in x dx. Well, that is the slope. It's also the derivative if you make the delta x and the delta y really tiny and call it dx square root of 1 plus the derivative of the function squared. So we can find the length of an arc between 2 places related to the x. So my x on this, the one I asked about, would go from 0 to 2 of the square root of 1 minus the derivative of this. Well, this was y equals x squared, so its derivative is 2x, 1 plus the square root of 1 plus 1 squared plus 2x quantity squared dx. Now, you can do trig sub and solve this, and we did that in class, but you can also just pull out your calculator and figure out what this is. The trig sub, it gets pretty messy, But if you go to your calculator and type in the square root of 1 plus parenthesis 2x close parenthesis squared, and go zoom 6, that's probably more than I need. Let's go zoom 4, a little closer in, and I want to find the area under this curve between 0, second calculate the integral 7, the antiderivative from 0 to 2, and it says the length of the arc is 4.646. Now, why are we getting a different answer than I did in the other class? The derivative of x squared is 2x quantity squared. Did I write that in correctly? 1 plus the derivative squared dx. Yes, I did. So that's the length of the arc from here to there. Oh, I know why that is. Okay. So that was what we did on Thursday's class after we did some other things. So then on Friday, we talked about, I started off the class with, okay, what if we had y equals the sine of x? Curve looks like this. And it crosses at pi and at 0. And I said, what's the length of that arc? So this is Friday's lesson. So it'd be the integral from 0 to pi of the square root of 1 minus, this equation is y equals sine x. 1 plus the derivative of sine x is cosine of x. And so I just go to here, and I'll go to change this to cosine of x. Squared. And I want to find, second, calculate the area, number 7. Between, that's what this graph looks like, and I want to go from 0 to pi. So lower limit 0, enter, upper limit pi, enter, and it says the length of the arc is 3.1415, no, is 3.820. Okay, that's the number I was confusing with this one. That's the length of this arc. The length of this arc was 4.6. This is the length of this arc. Straight across is pi 3.14, but this way it's 3.82, a little bit longer. Then we got into the discussion about area enclosed by two curves. So now I'm going to draw the sine curve again, a little bit better. So this is 2 pi, and this is pi, and this is 0, and this is 1. And so we got the y equals sine x curve. And then I made another equation, do it in red, y equals negative 1/4 x plus 1. So it goes through 1 on the y-axis, and it has a slope of negative 1/4. So by 4, I would be at 0. Well, here's pi, so 4 somewhere here. This line cuts across something like that, where this crosses at 4. And I said, I want to know the enclosed area. So that would be, let's use this. That would be this area and this area. You can't tell that's much different. Nope, not that area. This area. The area between the two graphs. I'm already making a mess out of it. What other colors do I have here? I got a red. Okay. So, we already discussed in class that to find the area under a curve, between curves, you take the area under the big one, which would be all the way to the axis. So this would be the area under the blue curve. And I'm going to go just to there for now. And then I would take away the area under the red curve, which would be this area. And that would leave this orange area. I mean, you probably can't see the difference in the color, but that's what I'm trying to get. It's that encapsulated area. So it would be the integral of the top curve, the blue curve, minus the equation of the red curve. Because if I do the integral of this, I find the area under the line. If I do this, I get the area all the way to the x-axis under the sine curve. And if I want the difference there, and I would do that dx, and I'd have to do it from here to there. So I need to find those intersection points. Now I happen to have this graphed, these two, and the intersection point right there is 0.89.777. 0.89, 0.777. And this is 2.85. I just tapped on my mouse on Desmos, and 0.2888. And this point, where the end of the enclosure is 5.813, comma, negative 0.453. Now, the question that I posed in the class was, this part is pretty straightforward. This is going to be from here to there, and we're going to take the blue curve minus the under there. So it became from 0.89 to 2.85, the antiderivative of this. And you can just type this in your calculator and get a decimal approximation for this area here that's between the two curves. How do you deal with this where it goes down below the axis? And so I took this in pieces to talk about this, to help students understand what's going on here. So, in here, this is kind of small for you to see. Maybe I can zoom in. Okay. In this section right here, we have the area under the blue curve, which is positive, and we have the area under the red curve, which would go all the way to the axis, but it's positive. And so I would be wanting to take the red curve's area under the red curve minus under the blue curve. So I want to do the red minus the blue for this little piece. Then the next section, where this crosses at 4, what would I want to do? Well, I want the area under the red curve, which would be this, and I want the area under the blue curve, but I want it to be positive. But its height, if I think about this, when the integral is working, this is the width of a bar, and the functions are the heights. So the height here of a bar is just the linear equation, and the height of the bar on this side is the height of the trig equation. And since this one's negative, if I did the red height minus the blue height, that would be a minus height, and I'm subtracting it, it would be a plus, and I would end up adding these two, which is what I want to do, times the width. So in here, I want to do the positive number minus the minus, which would add these. And so I would do the red minus the blue all the way through this section. And how about over here? If I did a small width, if I found the antiderivative of the red curve, I'd find this value, or the y value. This portion would be this height, and it's negative. Not the antiderivative, just the height. And then the height for this one would be a negative value, but it would be the height of sine at this place, and it's negative. And this is negative, and if I want the difference, I would want to take, if I took the red one, I'd have a negative number, subtract the blue one, the sine value, and it's already negative, that would turn it to positive, and this would be negative, and they would subtract, and I would get this height with a positive value. So in here, I want to do the red minus the blue. Subtract this bigger negative, which makes it a plus, and the red is already negative, and so I would get a positive value. So it turns out that it doesn't matter whether the red is above the x-axis or below, or the blue is above or below. It's more important that you take the highest curve, in this case over here the red one, minus the blue one. Over here we did the same thing. We took the highest, the blue, minus the red. So to get the total area for this and this, I would do this integral, the blue minus the red, plus the integral for the rest of the way, 2.85 to 5.813 of the red minus the blue. And if I just type those into the calculator, I'll find that the total area. Those are easy enough. You could also do find the antiderivative and plug these values in. And same on here. It would still be approximate because this is only approximate intersection points of the graph. So I spent quite a bit of time on Friday trying to get this understood, that you always do the higher minus the lower. But then I proposed this one. What does this look like? Well, it has a y-intercept of 2, a y-intercept of 4, and a y-intercept of 6, and for bigger numbers than 6, like 7, 8, or 9, this is positive, so it goes like this. Something like that. And x equal 2 would be something like this. Now, this is the positive direction for the x-axis, which is kind of like my y variable. used to be on the other one, and this is my positive direction here in the y this way. So I have to kind of think about looking at this from the back and thinking about it turned x-wise, or I can just say I'm going to do the integral, and I'm just going to label these points as A, B, and C, so I don't have to worry about the decimals on them. And it's A high in the y, and B high, and C. So I'm going to do the integral from A to B to try to find this trap area. But that's going to be dy, and it would be the curve, all of this, I'll call it f of y, the function in terms of y, minus 2. It would be just this minus 2. That would be this enclosed area, plus then I would want to do this enclosed area, which would be the integral from B to C, and this is dy because I'm doing slices sideways horizontally. I'm going to be doing slices horizontally here, so they're going to be dy, and this time it's the one that's more positive is the 2 minus what this curve is, and that's f of y, or all of this. And you could type this into your calculator and get it. And you can find these intersection points by doing it on Desmos. Okay? So that's doing things sideways. So then the book had an example. Let's see, I'll pull it up here. It kind of reviewed the area between two curves, but then it came to an example here that I want to talk about. So we got a sideways parabola and a line. X equals y squared minus 1. And y equals x minus 1. So drawing that, y minus 1 squared, x equals y minus 1 squared. That's a sideways parabola. And x going through minus 1, slope of plus 1. And so it meets out here at 3, 2, I believe. And that's at 1, 2, 3, and minus 1. And anyway, they want to know how we could get the area on that. Okay. Now, the easiest way would be to do the line minus the parabola doing slices sideways. So if I do a slice this way, the bar's width will be a little change in y. We're going to do this a lot, so you're going to have to get used to this. So the width of the bar is y, dy, and we're going to be doing the integral in terms of y. And so we want to use this sideways equation, and the farthest one over, we'd have to solve for x, which would be y plus 1. That's the line, minus the curve, which would be y squared minus 1. So you take the most positive one minus the least positive one. And we'd integrate from the y would go from -1 to 2. And that would give us the area. Now, if you tried to go the other way, it gets a little bit complicated. If you tried to do a vertical bar, so let's say I do one right here. Now the width of the bar now would be dx. Its width is a little slice of x. And we'd have to take this curve minus this curve. What's the same equation? How do we get two curves? Well, and we need to solve for it in terms of y. So if I take this equation and solve for y by adding 1 and taking the square root, I would get y equals plus or minus the square root of x plus 1. This side of the curve is the plus square root of x plus 1. This side is the minus of the square root of x plus 1. So to find take the top one minus the bottom one, to find the area between, I would be going the antiderivative, or the top one, minus the bottom one, and the bottom one is negative square root of x plus 1. So I'm subtracting a negative, and the widths are dx. I'm subtracting negative, so it's like adding it again, and so I have the integral of 2 of the square root of x plus 1's dx. And I want you to see what this means. And of course the limits would be from, now I'm doing x's, and they would go from -1 to 0 for just this part. But if I pull out the 2, this would be the area here under the positive curve to the x-axis, would be this. And if I double that, like it says to, I would get this and that and get the area of the whole thing. So this is the same as doing just double this. Anyway, I have to do this complicated stuff here for this piece, and then for this piece it would be the square root of x plus 1 minus x minus 1. That's the low curve. So I take the top minus the bottom one and do the integral for the rest of the way, which would be from 0 to 3 dx. And that would give me this area, and this, with that 2 pulled out here, would give me the area of the nose here. And so if I do vertical slices, I have to do it in 2 pieces. If I do it in horizontal slices, like I was doing here, little horizontal bars, I only need to do 1 integral. So how you set up your integral makes a difference in how complicated doing the problem is. And that's what they wanted you to understand. And that's enough for you to be able to do the homework in 3.1 if you understand it. So we'll see on Tuesday when we get back.